Okay. So the exam will be this Friday, will be when it opens up. And then you can take it at any point Friday, Saturday, or Sunday by the end of the day. So you kind of have 3 days there to kind of play around with when you want to do it. We will do review over the practice exams next class and then Friday as well. If you have any questions as you're going through those, please feel free to reach out to me. If you want to do a Zoom meeting or want to schedule time to stop by my office, that works as well. It's going to be a lot of hypothesis testing. It's going to be kind of similar to the format of the last exam, where the majority of it's multiple choice. But there might be 1 or 2 short answers at the end. On those short answers, kind of same thing. You upload all your work, show everything that you've done. For those, to get kind of full credit, like if you just give me, a test statistic and don't show any of your work for those questions, you're not going to get kind of full credit there. You need to show me all of your work. Other than that, you'll have kind of those practice materials that are up there on Canvas. You've got that formula sheet. Are any questions about that? And next class, I'll have kind of more of the details, playing around with kind of the couple questions to give you the exact number of questions as well as kind of the exact kind of time that you'll have. I'm thinking roughly probably about 90 minutes, so an hour and 30 minutes there once you start it to when you have to submit it. I don't think time should be just as much of an issue as it was on the first exam. I'll kind of plan that whatever the difficulty of the exam is, if you struggle kind of with time on the last one, that'll be something to be more conscientious of on this one, because it's not like I'm kind of writing it with the idea of there being any more or less time than the previous one. Okay. Any other questions for me before we get started today? No? All right. So I think last class we'd ended kind of on this proportion example. We worked through a few. I might revisit this if we have time today. If not, we can also save it for Wednesday, but I just want to make sure those slides were in there. So we did confidence intervals and hypothesis testing with 2 population proportions. The class before that, we did it with 2 sample means where we knew the population variances. So today, we're going to look at confidence intervals and hypothesis testing when we don't know those population variances, okay? So once again, it's not going to be a lot of new principles. It's just going to be kind of slightly tweaked from what we were doing with one population, okay? So if we don't know that population variance, we have to use a student t-distribution, just like before. It's almost normally distributed, but not quite. That was kind of the idea of the student t-distributions. So we're going to try to build confidence intervals for what that true difference in the means are, just like we did before when we knew the population variances. But now our confidence interval equation is going to look a little bit different, right? The only thing that changes from what we had done before when we had sample means, 2 sample means, we're still going to look for the difference between those 2 sample means. We're going to build our confidence interval around that for where that true population difference lies. Except for now, instead of using a z value coming from a standard normal distribution, we're going to have to use that student t distribution. Okay, so we're going to have to know what our degrees of freedom is. Now, it's not going to be as simple. Remember before, all we had to do was what? What did we do with one population to find the degrees of freedom? We just took the sample size and subtracted 1, right? It's pretty easy. Right? Now we're going to have a slightly different, kind of more complicated way to do that, but it's still the same process. We're looking for that t-value for our assigned degrees of freedom that gives us alpha over 2 on either side of that confidence interval. We're still multiplying by the standard deviation of the statistic we're interested in. It's just now the standard deviation for the difference in sample means is going to be a little more complicated. It's going to look just like it did before when we had 2 populations and sample means, but instead of using population variances, now we just have sample variances, right? Once you plug the numbers in here, it's going to look no different than what we were doing when we knew the population variance. So how do I now find my degrees of freedom, right? You might think, well, I would simply add up each sample size, right? And then maybe subtract 2, or maybe I add them up and subtract 1. So how many degrees of freedom? All of them. But actually we have a much more complicated way we have to find degrees of freedom here, because it's going to depend not only on the sample size, but what the variance ends up being for each sample. Now, don't write this down. I don't want you to look, this is a ridiculous equation, right? There's a lot of things in here. I mean, I could make you find this on every single example. At that point, I'm just making sure you know how to use a calculator, right? Like this is just a matter of getting this entered in with the parentheses correct, right? So in any of the examples that I give you, I'm going to, on the exam, give you an assumed true degrees of freedom, right? I'll tell you what it should be. Right? In practice, we would actually have to use this formula, plug in the two sample sizes, plug in the two sample variances, and figure out what this degrees of freedom is. If it's not an integer, remember that student t-table, the degrees of freedom are 1, 2, 3, 4, 5, 6, right? They have to be integer values. So in practice, if we did this, if we got a decimal, we would always kind of round it down or push it down to the lower degrees of freedom, right? Kind of erring on the side of caution, right? Because the higher the degrees of freedom gets, the closer that student t-distribution gets to a standard normal. Remember, we look at that student t-table. If we go all the way down to an infinite degrees of freedom, we're at that standard normal distribution, right? So we'll err on the side of caution and round down our degrees of freedom, okay? Now, like I said, in practice on the exam, I'm going to give you that degrees of freedom. I'm not going to make you calculate that. First of all, it'll take quite a bit of time, and like I said, just the exercise in using your calculator. But the steps of what we're doing are going to look no different than what we did before, other than that degrees of freedom is hard to find, right? But I'm going to be giving that to you so that we shouldn't have to worry too much about that as we work through these problems. And then once we have that degrees of freedom, we don't go to a standard normal distribution. We're getting these values that we need to build our confidence interval, these t values from a student t distribution. Okay? But then from there, it's a matter of plugging and chugging, right? It's going to be exactly what we did before, two populations, and looking at the difference in sample means. We're going to build our confidence interval around that difference. Just now we use this t value, right? So if we have this example, right, this is going back to kind of the last week's slide. It was our motivating example of maybe I want to know what is the true difference between the response time of people who are texting and non-texting while driving, right? So I've got texters as kind of text and non-texters as NT here, right? So I take 49 drivers who were not texting and I find their average response time. Maybe I have this set up on some track and I find that the mean response time of non-texters was 1.3 seconds. Sample variance for them was 0.16. I then look at a sample of 64 drivers. I find the sample mean response time for them, and those 64 were texting, was 2.36. Sample variance 1.44. What's the 90% confidence interval for the true difference between the response time of texters and non-texters? So I have this set up. This is a question last week. You'll always kind of be able to identify what group is one because I'm kind of telling you here, right? I'm saying we're looking for the true difference between non-texters and texters. Right? So if we think about what this confidence interval is going to be centered around, we go back to our equation. Remember, it's centered around, we're now interested in the statistic of the difference in our sample means. So here, I've got my non-texters response time, my texters, I just look at the difference between those two. So what, 1.3 and 2.36? I don't want this one. So I can think about this as group one, kind of in the more general equation, and group two, I had what, 1.3 minus 2. See if I got those numbers right. Is that what they were? Yeah? Okay. So I'm building this around what? Negative 1.06. Right? So I know my confidence interval that I'm creating will be centered around that value. I'm then going to go a certain amount to the left and right to get my lower and upper bound. How much am I going to the left and the right? I'm going to use that t value, right? That gives me alpha over 2 in the tail. And then here, multiply by each group's sample variance divided by that group's sample size, where this represents, and actually I guess if we're going to write this notationally correct, kind of the standard deviation using sample variances for the statistic of the difference in those group sample means. Okay? So here I'm just going to be plugging my values in. I was given those directly from the problem. The only thing left I really need to do is look up that student t value. So I want alpha over 2 in the tail. At the 90% confidence level, alpha would be what? I think someone said it. 0.1, right? So I divide that by 2. I want 0.05 on either side. Right? So go to that student T table. Now the problem here is I also need my degrees of freedom, which requires that crazy equation, right? Well, I plugged everything in there for you. We get 80.39. We'll round it down. This kind of delta represents our degrees of freedom. We're looking at these two population examples. So our degrees of freedom here is 80, right? So, I didn't want to do that. There we go. So I'll go to my student T tables. My degrees of freedom is 80. The area I wanted in the tails, we said was oh, come on. It's because I did this here. I have to reopen this real quick. Sorry. It's not going to like that either. There we go. So the area I wanted in the tails was 0.05. Okay. All the way down at degrees of freedom of 80, 1.664. Right? So 1.664 is the value that I want to use. Right? So this guy right here is the only other thing I needed, 1.664. I plug in my values. Now it's just a matter of getting that entered into my calculator correctly. So it's using we're using that T table the same way, we're plugging things in to a confidence interval equation that we'll have in front of us. If we do this, well, we should end up with, I can get this going here. All right, plug everything in. We get a confidence interval of about -0.133 to -0.79, right? So if you could stop texting and driving, that'd be great. I won't say it like the character in this movie, but if you all haven't seen Office Space, you definitely should. It's a hilarious movie. So we've got this confidence interval. Let's start to do some interpretation, like why is this maybe interesting? Well, if I think about -1.33 to -0.79, so was it 1.33 to -0.79, right? With 90% confidence, what could I say here? Remember that kind of our group 1 was non-texters and group 2 were the people who were texting while driving, not texting while driving. With 90% confidence, what could I say here? So this confidence interval represents what? The true population difference, possible values that with 90% confidence, I can say the true population difference between response times of non-texters and texters lies somewhere in this range. What's true about all the values in this range? They're all negative, which means with 90% confidence, I could say that people who aren't texting while driving actually have lower response times. Right? If that difference is negative, then this number has to be less than this one. Right? And so I can say with 90% confidence, the response time of non-texters, right, is lower, which is good, right? You can respond quick, right? A lower response time means I'm responding quicker. Right? So anytime we have a confidence interval that doesn't cross over that 0 threshold, we can start to say some interesting things, right? Now, if this instead had been positive 0.79, I can't really say much because the true difference could be, if this was the thing, could be 0, which means there was no difference, right? So anytime we have it though, that wasn't the case here. Anytime we have it where all the values are negative or all the values are positive, we can start to say some pretty interesting things, right? We had some sample evidence that led us to be able to make some useful statements about what the true population difference is, okay? Any questions on that before we keep moving? I know there's a glare here on the video, so if you guys on Zoom can't see this, this should just be, I've got up here, this was the standard deviation of our difference in sample means. Okay. Any questions on that? Okay. So we'll go through another example here. There you go. So let's say we had 2 different brands of cigarettes, and we're interested in whether or not one has a higher level of nicotine than the other, right? Maybe, I don't know, maybe we're trying to do some regulation, or we're trying to figure out, which, maybe if I don't know, Maybe if I'm trying to attack big tobacco, I choose the one that has a higher one. So I want to know what are the true values for the differences in these brands, right? So I've got 20 brand A, 25 of brand B. So those are kind of like my two sample sizes of the groups. I've got my two sample means. So this one, brand A, has a little bit lower nicotine levels. I've got my sample variance as well, right? So those are the 6 things that I needed to kind of plug into that confidence interval equation, right? If I think about the other thing that I needed was that student t-value, right? That gave me alpha over 2 on either side of my interval. So if I want to do a 95% confidence interval, for what the true difference is in between the population means of these nicotine levels for these different brands, and this is how I would kind of phrase or kind of set this up on an exam, and then I give you what that degrees of freedom is, right? So that delta that we're supposed to be calculating using that crazy big formula, I'm telling you, if you plug the numbers in here, you get a degrees of freedom of 42, okay? So you have your degrees of freedom. You can think about, okay, what is the sample difference that I found? So 1.68 and 1.95. So it's going to be set up just like we had the other one, right? Just now, we're not looking at non-texters and actually, so we're going to be, I forgot my little bars here. You got brand A and brand B. It was 1.68 and 1.95. So we get what? Negative 0.27 here. So my confidence interval should be built around that sample difference that I found, right? So I know it's going to be centered around negative 0.27. So even if I do no more work other than that, I can rule some of these out right away. For one, I can rule out B, right? It only has positive values. Well, the sample difference I found was negative, and it has to be centered in the confidence interval, so it's not even in this confidence interval, right? I think so. I had negative 0.27. If I look at these other ones, I think it's centered in all of them, it looks like. So can't really rule anything else. Actually, would it be centered here? No, it's not even in this confidence interval, right? Or no, sorry, that's 0. Sorry, we had negative 0.27. So if I think about here, I can rule out A as well, because it's negative 0.27 in this range. No, right? It stops at negative 0.058. I have to keep on going, right? So just by thinking about what my confidence interval is centered around, my sample difference I found isn't even in the confidence interval that I have for A and B here. So right away, I know I'm going to be between C and D, right? So I have everything I need to kind of plug in. There we go. To plug into that equation other than this t-value, right? So how do I find this t-value of 2.018? Well, I was given that degrees of freedom of 42. At the 90, what was it, 95? My computer's going slow for some reason here, and then it's jumping ahead real quick. All right, this is bugging me. Okay, so where are we at? Here we go. If we have the 95% confidence interval, my alpha would be 0.05, but I want alpha over 2 on either side, right? Alpha is the total area outside my confidence interval. So 0.05 divided by 2 is 0.025. I'll go to my table. I want 0.025 in each tail, right? So that's the value I'm going to look up. I go down to degrees of freedom of 42. The t-value that would give me 0.025, kind of in that upper right tail, which would mean if I subtracted it and look at negative point, if I wanted 0.025 in the lower left tail, it would be this value, but negative. That t-value would be 2.018. Okay? So that's how I find that t-value that I need to use in my confidence interval equation. Right? So I go back to my problem. I now have that t-value, and now it's just a matter of plugging and chugging, right? Getting everything entered into that confidence interval equation, okay? Like I think I mentioned last week, if you're having difficulties once you're trying to put this in your calculator, maybe try working backwards. That sometimes can help if you're not trying to like put parentheses around everything. If you're just putting parentheses around everything, you should be able to enter it all in at once and be okay. But if you're doing it kind of line by line, so 0.06 divided by 25, hit enter, plus 0.04 divided by 20, enter, take the square root of that, kind of working backwards like that if you're doing it one step at a time. Any questions on just kind of the process here? I think, like I said, it's stuff we've already done, right? Just a slightly kind of longer, more complicated formula. And I'm really kind of punting on the part that really sucks about these problems, which is finding the degrees of freedom, right? I'm kind of giving you that because it's just an exercise in entering that into your calculator. In fact, I probably won't go through them prior to the exam, but you can imagine, I showed you how to do all of the hypothesis testing and confidence intervals with one population in Excel. You can do the same thing for two. It's just slightly longer equations in there. You'd still be using the T dot I and V function here, right? And, you know, to put that degrees of freedom formula into Excel, as long as you get it in there right one time and you reference like where your sample sizes and where your sample variances are going to be, you only have to enter it in there one time and you can always kind of get it, copy and paste that to be pretty easy. But that's why I'm going to give you this assumed true degrees of freedom. Oh, you have a regular, so F4, but if you have an FN key, you would hold FN and hit F4. Yep. So we've got this confidence interval. Once again, why is this an interesting confidence interval? All the values are negative. So with 95% confidence here, we could say that brand A has a lower nicotine level than brand B, right? Because all of the values are negative. So with 95% confidence, I know the true population difference is a negative value, which would mean that my group 1, which is brand A, has to be lower than group B. Right? Now, I can say that with 95% confidence. What if I wanted to say it with 99? I might be able to, but what's going to happen to my confidence interval if I want to say something with a higher level of confidence? It's going to get wider. So it might get a little bit wider, but I mean, we were at what, negative 0.4 and negative 0.1. My guess is if we go up and look up the t-value and kind of redo our confidence interval for the 99% level, it probably does get bigger, but my guess is it probably doesn't get wide enough to kind of overlap 0 there. You probably still have all negative values, right? But if it did cross over 0, then, you know, we couldn't say with 99% confidence that it had a lower nicotine levels. All right. Any other questions on that before we keep moving? Where are we at? Oh, we got plenty of time. Okay, so what if we want to do a hypothesis test, all right? Well, I don't know what that population standard deviation or population variance are. It's going to be very similar to what we did before. We had 2 sample means and wanted to know what the true population difference in the means was. It's going to be all the same steps. It's just now, just like with one population, when we calculate our test statistic, it's a t statistic because it's coming from a student t distribution. And when we look up our critical values or want to find our p-values, we have to use that student t distribution, which now requires delta, which represented our degrees of freedom, right? That kind of crazy equation, okay? But all the steps are exactly the same, right? So what does our test statistic equation look like? Once again, this will be how we find degrees of freedom, but I'm not going to make you do that. Here's our test statistic equation. It looks exactly like what we did last week. It's just instead of population variances, we have sample variances for the 2 groups. Okay? So no different than what we were really doing before, other than we're using sample instead of population variances. So our test statistic now doesn't come from a standard normal or the Z tables. It comes from a student T or the T table. So we call it, instead of a Z statistic, we'll just call it a T statistic. I think I even mentioned last week, we're not going to do anything before the exam with this, but like we can have things coming from an F distribution, which would be an F statistic, right? So it's just kind of notating like what distribution it's coming from, okay? And it still represents kind of the number of standard deviations away that the sample statistic we found, or the sample difference was, from that assumed true value. Right? So let's say we had a problem like this, put some actual numbers to this, where we want to say, do male and female physicians earn a different salary, right? So we sample 41 male, 41 female physicians. We find the sample, average salary for the male physicians to be 174,000. Huge sample variance there, 49 million. And then we find kind of the sample mean for female physicians to be 141,000. with a sample variance of 36 million. Okay? So what would my null and alternative hypothesis be here? Well, if I'm not, at this point, it doesn't even matter whether or not I'm thinking about male minus female doctor salaries or female minus male. Here I'm just thinking about if they earn different salaries, I want to know, is that difference anything other than 0? Because if they were the same, when I take the difference, they would be equal to 0. So if I'm wanting to test for whether or not they're different, what I'm saying is if I looked at that true population mean for male physician salaries and that true population mean for female salaries, if I took the difference of that, is it anything other than 0? Right? Are they different from each other? Right? I'm not even saying is one higher than the other, is one lower. I'm just saying, are they different? So I'll assume the opposite is true, which is that the difference is equal to 0. I'll assume they make the exact same salary. Right? So I have what type of tail test here? Two-tail, a not equal to sign in the alternative. So it's a not equal to or two-tail test. I've got my 2 sample means, my 2 sample variances, my 2 sample sizes. That's everything I needed here, because now my assumed true value for the difference is just 0. And I said that's always what it'll be. It won't always be a two-tailed test. Might be that is the difference greater than 0, which might make sense here, right? Like if we're testing for whether or not males make more than females or vice versa. So you could have, not always a two-tailed test, but it will always be using this assumed true difference value of 0. So this part of our test statistic equation essentially isn't there for the examples that I'll be giving you. Right? Now we could do something like, is the difference between male and female salaries not just not equal to 0? Is it something other than, I don't know, if we want to do like greater than 30,000, right? We could do something like that, but I won't give you examples like that in this class. But outside of this, if you wanted to, we could kind of push it and use values other than 0 there, which would just make it a little bit more complicated, right? Look a little bit more like what we did with one population examples. All right, so we've got everything we need for a two-tailed test, okay? So what we're really doing here is just to kind of set up hypothesis test examples again for us so we can remember what it looks like. I've got the statistic I'm interested in. I'm looking at the distribution of the difference in those sample means. Right? So I've assumed the difference is equal to 0. So if in fact that is true, my distribution for the difference in sample means I should be centered around that value of 0. I think if I looked at that, what did I find? What were the 2 sample means? So 174,000, 141. So if I look at the sample difference I found, it would be what? 33,000, right? That's the difference between those 2 values. So I found sample evidence that this difference is 33,000. If I'm thinking about the true difference was 0, right? It would have been equally as likely for me to see that same distance away from the assumed true value, but below it for a two-tailed test, because now this evidence would go against the null, right? Evidence on either side here goes against the null because all I did was say, I assume it's equal to 0. So if I find that the difference is positive or negative, it still goes against what I assume to be true. So my total p-value would be the area kind of in both of these tails. Now, this is what I'm going to be building my test statistic off of because this is the sample evidence I found. So I've got half of my p-value in each tail. Once I find this area, I multiply it by 2. That would give me kind of the total p-value I want. Right? So that was kind of that additional step we have for a two-tailed test. Once I find the area to the right, if I have a positive test statistic, or the area to the left for a negative test statistic, right, I had to multiply it by 2 because I have 2 tails here. Right? Evidence on either side would have went against the null. So what I'm going to have to do, if I use the p-value approach, is I could turn this into a test statistic or a t-statistic, use that to find the area to the right using the standard normal table, and then multiply it by 2. Okay? So how do I get that test statistic? We had the equation. We've got everything we need. We have the 2 sample means, 2 sample variances, 2 sample sizes. So let's just go ahead. Oops. Skip the critical value approach for right now. So let's just say I go ahead, I plug all those values in, I get a test statistic of about 22.9. This is ridiculous, right? This is a huge test statistic, right? But think about why. We assumed that the true difference was 0, right? We've got decently high sample sizes. I found a sample difference of 33,000, right? If I assume it's 0, and then I see a sample difference of 33,000, I mean, that's pretty inconsistent with what I assume to be true, right? So it's not crazy that we got such a high test statistic. Now, I mean, it leads to, automatically, what do you know the p-value is going to be close to? Yeah, something like 0, right? I mean, if I think about, if I tried to find the p-value using the table, I mean, I could find what my degrees of freedom is here by plugging everything in that equation. I'll tell you right now, it's going to be close to 80, right? I think it's actually, might be exactly 80. So if we assume it's 80, oh, I didn't want to do that. I always hit the wrong, I don't know why my brain's wired like that. So we go to that t-table and we assume that the degrees of freedom we would find is 80 using that kind of complicated formula. We go down to 80. Well, the area to the right of 2.6 is 0.005. So if the area to the right of 2.6 is 0.005, the area to the right of 22 is going to be essentially 0, right? Well, we have two sides. One side is almost 0. The other side's almost 0. If I add them together, my p-value is going to be almost 0, right? With such an extreme test statistic, I mean, if I look at this, right, I mean, even if I had a really small sample size, well, and one's, we're never going to have a sample size of 1. That's just insane for the examples we're doing. But like, even with a sample size of 2, we'd have a crazy huge test statistic. The p-value is still going to be 0, right? So with such a high test statistic here, our p-value will be approximately 0. And we could actually put this into Excel. So we have our t-value. We could do t.dist, right? Actually, we could do t.dist.2t. That was the two-tailed one that would tell us kind of the total area in both the tails. Put in our test statistic, put in that degrees of freedom, which is, like I said, it's going to be 80. And it would probably show you 0. It might be like something e to the negative, 80 or something like that. But it's going to be essentially 0. So if the p-value is pretty much 0 here, what levels could we reject at? If I'm looking at the 1, 5, and 10% levels, the p-value of 0, I can reject every single one, right? Because remember, I would definitely have this written down going into the exam. We always reject if the p-value is less than alpha. If my p-value is 0, it doesn't matter what alpha is, 0.1, 0.05, or 0.01, my p-value is going to be less than that, okay? Now, if I instead, it's kind of tough using that t-table when we want to do the p-value approach because there's only like 6 test statistics that could be for any 1 degrees of freedom. I said last week, it's probably easier to kind of first find our critical values and then plot our test statistic against them if we're using a student t distribution for hypothesis testing. So what do I want to do with these critical values? So I want the critical value that gives me alpha total in the tails. But remember, I have a two-tailed test, so I'm actually going to have 2 critical values or a pair of critical values at each alpha. And essentially, I would have alpha over 2 on each side of that distribution. So if I start with alpha is equal to 0.1, I divide that by 2, we get 0.05 on each side. If we use that assumed true degrees of freedom that I said we would have found of 80, right? What would our critical value be there? Well, we assume that the area in the tail we want is 0.05, right, in each tail. So I scroll down until I get to the degrees of freedom of 80, 1.664, right? Same value we found for confidence intervals, but just coincidence there. So 1.664, right? So when I think about visually what I'm looking at there, negative 1.664 and 1.664 over here. I draw arrows kind of to values that would be more extreme or larger in absolute value, or just draw arrows into the tails. And now if my test statistic of 22 is plotted over here, clearly it's in the rejection region, right? Now we could look up the critical values for an alpha of 0.05 and an alpha of 0.01. For a two-tailed test, we'd have to kind of divide that by 2, so 0.025 and 0.005. In fact, if I was doing it and I wanted to test against all 3 levels, I'd just do this all at once, right? I know that I want to find alphas of 0.1, 0.05, and 0.01. I'll have to divide all those by 2 because it's a two-tailed test, so 0.05, 0.025, and 0.005. So these are the 3 columns I want to find my critical values for each of those alphas. Go to my degrees of freedom of 80. So we already found this one. I want to look at an alpha of 0.05. The critical values I would need would be negative and positive 1.99. And then for an alpha of 0.05, right, gets divided by 2. So 0.005 is the area 1 each tail. The critical value would be positive and negative 2.639. We could plot those up on that graph. I mean, I'm going to kind of run out of room probably here, but you can imagine like we had what, I already forgot what I said, 9 something and 2.6 something. This might not be 1.9. What was this? My memory's going. Oh yeah, 1.99. So 1.99, 2.6, negative 1.99, negative 2.6 something. I mean, it doesn't really matter, right? Test statistic of 22. I didn't draw this to scale, right? If I really wanted to plot this to scale, my test statistic is going to be like way over here, right? So clearly I can see here, I'm going to be rejecting at all 3 levels. Just like when I did the p-value approach, I was clearly rejecting at all 3 levels. Right? Any questions on that before we move ahead or feel comfortable with that? All right. Okay. So that kind of finishes up. If we're thinking about just the 1% significance level, that was at 2.6, but we could look up all 3, right? I want to kind of make sure we know how to do this against not just one level, but multiple at the same time. Okay. All right. So I want to go through this. I don't know if I have enough time to completely work through this today. What do I want to do? I'll go through this. I think we can do this. So let's instead assume that we want to do a problem. And I'm just going to use these numbers to kind of prove not as much of an interesting question, but I want to show you some. So if I look at the difference between 3 and 4 here. So let's use examples 3 and 4. Right? So I find a sample mean of 70. I've got my sample standard deviation, which if I wanted the variance, I could just square it. Right? Got my sample size, and I've got this assumed true value of 73. Okay? So let's think about this first example, what that would look like. I've got this distribution of sample means. I assumed the true mean was 73. I found 70, right? If it was a two-tailed test, it would have been equally as likely for me to see a value up here at 76. So my total p-value is kind of the area in both these tails. So each would represent half my p-value, right? Now, I'm not going to work through this example completely because I want to show you some other things I think are more interesting that I want to make sure we understand. I could turn these, calculate my test statistic, go to that student t-table, probably can only put bounds on my p-value, or I could use Excel and find exactly what my p-value is. But whatever my p-value ends up being, right, let's think about what would happen to my test statistic equation if instead, oh, actually, sorry, this is a 2. I'm going back to a 1 population example. So we have sorry, I'm switched gears a little bit here. I forgot. I'm using a 1 population example to kind of make this point, right? So it's still a two-tailed test, comes from that student t-distribution. If I wanted to calculate my test statistic here, I could, and then find my p-value. Right? What happens if I move from problems 3 to problem 4 on that last slide that I had had up there. So problem 3, everything's the same, but I took a higher sample size in problem 4. So what happens if I take a higher sample size? If I take a higher sample size here, what happens to my standard deviation of the sample mean? Right, that's what the denominator represents. What happens to kind of this guy if my sample size goes up? It gets lower, right, because the denominator is larger. If I have a smaller standard deviation or variance on my sample means, we know that that would make it, here, I actually should probably draw this way more extreme to prove this point, right? It's going to make that distribution of my sample means more peaked because the variance of the standard deviation is lower. So now if I see that same sample evidence, what's happened to the p-value? It's gotten much, much smaller, right? And that's because I'm the same distance away from that assumed true value, but if my standard deviation is half as large, I'm going to be twice as many standard deviations away, right? Or it's way less likely that I saw that same value, excuse me, that was that distance away from the assumed true mean if my sample size was larger, right? And so this is kind of where the power of taking higher sample sizes gives us. Now seeing that same sample evidence, I'm going to end up with a smaller p-value. Or I'd be able to reject potentially a value now that I couldn't before, because think about what happens to my test statistic. Well, now I know the denominator is smaller, so my test statistic will be higher. If my test statistic gets higher, if I had drawn this out, right, it's moving kind of into the tail, my p-value gets smaller. We already kind of had that visual. If my p-value is smaller, am I more or less likely to reject the null? If I reject when the p-value is less than alpha, if my p-value is getting smaller, am I more or less likely to reject the null? So, right, if this p-value is getting lower, if I take higher sample sizes, potentially, before, let's say my p-value was 0.06, I couldn't reject the null, right? If I take a higher sample size, I know that's going to increase my test statistic, decrease my p-value. Potentially now, my p-value is 0.04, and I could reject the null. So we say, when we take a higher sample size, we get higher test statistics, lower p-values, which means we're more likely to reject than we were before, right? Because now seeing that same sample evidence goes against that assumed true value with even more intensity, as you want to think about it that way. Okay? Any questions? And if you're kind of writing this down, it may even make sense to kind of, as I was going through this, like step 1 or like to follow kind of the line. Sample size goes up. You could even skip this step if you really wanted to, but test statistic also goes up, which means p-value goes down, makes me more likely to reject the null. And everything would work in reverse if we had a smaller sample size, right? Any questions over any of that? Okay with that idea? Another thing I wanted to point out here is, let's say instead of finding that sample mean of 70, everything else was the same. So let's say we go back to problem 3. Instead of now taking a higher sample size, the sample mean we found wasn't 70, but it was instead 76. What would change for a two-tailed test here? Well, if I was before, I had a sample mean of 70. So when I turn that into a test statistic, what will be true about that test statistic and the test statistic I find for 76? Yeah, so remember, even if it comes from a student t or a standard normal distribution, our test statistic is a z or a t value, which represent the number of standard deviations away from that assumed true mean. So if I'm 3 away from that assumed true mean, below it, I'll find negative, let's say, I don't know, 2.5. Well, if I'm 3 above it, that would be positive 2.5 standard deviations above, right? If it's the same distance away from that assumed true mean, it's just going to be the same test statistic, but this was evidence below the assumed true value, so it would be a negative test statistic. This was evidence above it, so I'd find a positive test statistic. When I do the two-tailed test, symmetric distribution, the area to the right of 76 is the same as the area to the left of 70, so whichever one I find and multiply by 2, it's going to give me the same answer, right? Which, if it gives me the same answer for my p-value, I'll make the same rejection decisions, because either one of them was equally damning evidence against that assumed true value. It was just as far away. And if I don't care about what side I'm on, right? If I just want to know, is it different than 73? Well, this was evidence that goes against that equally as much, right? Any questions on that? Does that make sense? So those are two things I wanted to point out. And like I said, we didn't really use those numbers and go through it. If you really wanted to prove yourself, you could like calculate the test statistics for those different sample sizes, calculate the test statistics for these two values, find they're going to be the exact same, right? So I just wanted to more so use that to point out those principles. Okay, and then I thought this was a great meme that I haven't gotten to use yet. So I got 99 problems about rejecting the null hypothesis ain't one. I also want to show you one more thing that I think is really relevant. It'll probably be like the last presidential stuff I'll show you after tomorrow. I guess it doesn't matter. So I don't really care about, I care about the election. I shouldn't say that. But I'm much more interested in like kind of this, like all these polls, the statistical stuff that's kind of surrounding it. So everybody wants to say like these polls are wrong, these polls are right, blah, 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 blah. So I was actually looking at, and I think CNN was kind of referencing this 270 to win. And they kind of do a collection. So here's Georgia. They'll show you some of the major polls that have been done, what the numbers were. And then they'll take kind of the most recent ones and kind of do like an average of them. Well, I thought this was interesting because like I was just kind of interested in like, could I use this somehow to predict like what states, use it for a confidence interval example or something. Well, then I started looking at the data, and this goes way back to something we talked about a long time ago. So if I download this data, pull it up here. So here was the Georgia data. I looked at these and I noticed they were taking the average of these 5 recent polls. And I realized all they were doing was taking the average, right? They were presenting these numbers, they were just taking the average. But if I look at the sample sizes, which of these polls should I definitely pay way more attention to? The one that has 1,700 people as opposed to like 5 and 700. So we probably want to do something more like a weighted average across these 5, right? So if we do that, notice this race where it was only 0.2% kind of apart in Georgia. If I actually do a weighted average, I'll change these to a percent just to kind of show you. Notice it's not 0.2% away, it's almost a full percentage point, right? 47 and 48. And then North Carolina, you have a similar issue, but instead, right, the amount they report's really close. This is actually even closer than 0.2. It's like 0.06 or something away, right? So I think it's just a good example of how when you see things portrayed, like when you see numbers, like think, how did they get those, right? Because all the numbers they're showing you here, these averages, all they did was take an average of these 5 polls. 1,700 is a way larger sample size than 500. We should definitely be placing a higher weight on the results we see from that poll, right? There's also some interesting like bias issues we could look into. Like, I don't know how all these polls were necessarily done, but also there's some that included third parties and some that didn't. Well, that's drastically going to skew kind of the, we're eliciting certain responses if we eliminate third party candidates when we know that some of them are polling at 3 or 4%, right? So I thought it was just like a good example of some old things that we talked about. It's pretty relevant. I don't know. Who knows what will happen tomorrow? Maybe the world will end. So anyways, I'll end it there. We'll go over stuff on the practice exams on Wednesday. If you have specific problems, bring them to class. I'll start with those. Otherwise, I'm going to kind of pick and choose, but I think it's probably more beneficial if you guys kind of have some ready to go. All right?